All right, hello class. We'll be covering chapter 17 now, covering aromatic reactions. For an overview, again, we're covering reactions to aromatic compounds. Specifically, we're going to deal first with the electrophilic aromatic substitution reactions. Also, I like to abbreviate these as the EAS class of aromatic reactions. Okay, so there's 5 common types: nitration, sulfonation, halogenation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. All right, we're going to cover the reagents for each type, and also how to draw the major products from various reactants. Okay, we need to learn the mechanism and key resonance contributors, and we need to understand direct and group selectivity. Okay, so we'll talk about the positions first on benzene ring, in particular, the ortho, the meta, and the para position. Then we'll talk about these electronic effects, electron donating groups. I'm going to govern ortho and para positions, and electron withdrawing groups prefer to direct at the meta position. Okay, we'll talk about activators and deactivating, and electron withdrawing versus electron donating. Okay, and then we'll talk about competition among substituents. So there's multiple substituents on a ring. The competition will build up, and we want to be able to deal with that correctly. All right, we'll talk about these 5 cases and how to use that to predict the correct major product. And then at the end of this, we'll start to move into part 2 of this lecture, which is dealing with the opposite class, which is the nucleophilic aromatic substitutions. And lastly, we'll talk about reactions to substituents. Okay, so let's cover our 5 common electrophilic aromatic substitution reactions. But before we go into details here, let's discuss, or let's just review what exactly is happening in this reaction. All right, what are we substituting? Okay, and the best way to think about this is as benzene that has a potential of 5 hydrogens. We're just going to focus on one of those hydrogens. This hydrogen can be replaced by an electrophile. So we're substituting an H for an electrophile that we're just specifying as E. So if you want to think about a general mechanism of this, all right, the first step has to be an electrophilic attack. All right, keep in mind that electrophiles are seeking electrons. All right, because they don't have the electrons they need, the reaction arrow cannot start from an electrophile. Instead, the reaction arrow has to start from the benzene ring. All right, the benzene has the electrons that the electrophile are seeking. All right, so one of the pi electrons, or the pi electrons, I guess you would say, one of the pi bonds, these 2 electrons, are going to attack the electrophile. Okay, that's going to generate this carbon cation species. All right, and carbon cations to aromatic compounds are typically known as arenium cations. Okay, conveniently, this carbon cation has a few resonance structures. So step 2 here would be just resonance delocalization. All right, I have a lone pair, I'm sorry, not a lone pair, but you have a pi bond next to an electron deficient atom that can delocalize to generate this resonance structure. And then the neighboring pi bond again can be delocalized to generate this structure. Okay, so typically in reactions or electrophilic reactions to aromatic compounds, and specifically to benzene, there's going to be 3 main resonance contributors that we need to consider. The last step here is going to be a deprotonation. So we're going to have a conjugate base in solution that's going to pull an H, or going to pull a proton, and the corresponding electrons in that bond are going to form a new pi bond. All right, so conveniently, this deprotonation also regains aromaticity to the ring. All right, so that's a very favorable process to deprotonate there, because we gain back aromaticity, and we know that generating aromatic compounds is a very, very favorable, energy favorable process. Okay, so let's cover these 5 common electrophilic aromatic substitutions. All right, so we're going to start with benzene again. I can replace the H in benzene with an NO2. I need to use nitric acid and sulfuric acid mixture. All right, we call this class of reactions nitration. So again, benzene H is replaced by NO2. I need nitric and sulfuric acid to do nitration. All right, I can take this benzene ring and replace it with a sulfonyl group, SO3H, okay? I need to use sulfur trioxide and sulfuric acid. And this mixture is also known as fuming sulfuric acid, okay? We call this class of aromatic substitutions or electrophilic aromatic substitutions sulfonation. I can take this benzene ring and I can replace the H with an X. An X here, this means any halogen, so that can be a fluorine, a chlorine, a bromine, or iodine. The way that I do it, I need to have a halogen with a Lewis acid, all right? So I can have X2 with AlX3 or FeX3, all right? So these aluminum trihalide complexes or these iron trihalide substrates are very good Lewis acids that need to be present with the halogen. All right, the halogen by itself isn't appropriate to do these. All right, this class of transformations are known as halogenations. Okay, I can take that H and replace it with any R, and again, R means any carbon group here. All right, the way that I do this is that I need an alkyl halide. I'm going to specify that as RX, and again, I need that Lewis acid. These class of reactions are known as the Friedel-Crafts alkylation. Okay, and lastly, I can take that H and replace it with an acyl group. All right, that's a carbonyl group R, or a carbon group that has a carbonyl group attached directly to the ring. All right, the way that I do that, I need an acid halide with the Lewis acid, and this is known as the Friedel-Crafts acylation. Okay, so just to review, an acyl group again is the carbon, I guess the carbon functional group with the carbonyl. You need the carbonyl with some carbons, all right? And the R group or the carbon groups without the carbonyl are your typical alkyl groups, all right? So you're gonna get familiar, get comfortable with alkylation and acylation now being some terms that we use to describe different types of carbon functional groups. Okay, typically the first step in electrophilic aromatic substitution reactions are preparing the electrophile, preparing E+. Let's cover those mechanisms really quickly. So for nitration, sulfuric acid is a stronger acid and it will protonate nitric acid to form water. Okay, water is going to be kicked off the molecule to leave behind NO2+. NO2+ is referred to as the nitronium cation, and that is the electrophile for nitration. For sulfonation, one molecule of sulfuric acid protonates another. Again, I generate this oxonium cation that leaves as water. There's going to be a protonated oxygen species that becomes deprotonated by water to generate sulfur trioxide, and that's the electrophile for sulfonation. In halogenation, lone pairs from the halogen donates into a Lewis acid. All right, this causes a generation of a positive charged species that kicks off or breaks a bond between the two halogens to form a metal tetrahalide species and X+. And the halonium cation is the reactive species or the electrophile in halogenation reactions. In the Friedel-Crafts alkylation, again, I need an alkyl halide, and its lone pairs on the halide side donates into a Lewis acid. This causes the bond between R and X to break, leaving behind a tetrahalide metal and an R with a plus or a carbon cation. So the carbon cation is the electrophile in Friedel-Crafts alkylation. Lastly, in Friedel-Crafts acylation, the halide from the acid halide is going to donate into the Lewis acid. Again, that's going to cause the bond between carbon and halide to break, kicking off a metal tetrahalide species and an acylium cation. And I've drawn the two resonance structures out for the acylium cation, and that is the reactive electrophile for Friedel-Crafts acylation. Okay, so this review, And nitrations, I need to generate NO2 plus as the electrophile, and that species is known as the nitronium cation. For sulfonation, the E is just sulfur trioxide. For halogenation, it's X plus, the halonium ion. For Friedel-Crafts alkylation, it's just a carbon cation. And for Friedel-Crafts acylation, it's the acylium cation. Okay, let's do some practice. Can you provide the reagent needed to complete the following transformations for each? All right, I'll give you guys a few seconds to try. If you need to, please pause. Okay, for the sake of time, I'm going to move forward. Here's the answers. The top reaction replace H with NO2. That's nitration. I need nitric acid and sulfuric acid to do nitration. The second reaction substitutes an H for a Br. All right, so that's going to be a halogenation, and I can do that with Br2 with a Lewis acid, and I'm going to use here iron tetrabromide. Step 3 has an acyl group present. So I'm going to use the azo chloride here with a Lewis acid, and I'm going to use aluminum trichloride. All right, the fourth reaction is a sulfonation reaction, and I need foaming sulfuric acid, which is this sulfur trioxide sulfuric acid mixture. And lastly, I have an alkyl halide and a Lewis acid to generate the Friedel-Crafts alkylation product. Can you provide the products from the following reactions? Again, if you need more time, please pause. All right, for the sake of time, we're going to move forward. The first reaction is a Friedel-Crafts alkylation. However, there's a rearrangement here, and my product would be the isopropyl sustituent. All right, keep in mind that Friedel-Crafts alkylation generates carbon cations, and we know that carbon cations are always prone to rearrangements. All right, so this carbon cation will undergo a hydride shift to transform from a primary carbon cation to a secondary carbon cation. All right, the aromatic ring is going to attack that carbon to generate that product. All right. In the second reaction, this is going to be no reaction. Please keep in mind, chlorine cannot, or any halogen by itself cannot react with benzene. All right, you need a Lewis acid present. And for the last practice problem, can you guys provide the mechanism for the nitration of benzene? If you need time, please pause now. Okay, let's cover the nitration of benzene. First up, protonation of nitric acid to form an oxalium cation. All right, the lone pairs from a neighboring oxygen donates to make a bond while kicking off water. Okay, so now I form my nitronium cation. Benzene attacks that to generate my iridium cation. All right, my conjugate base deprotonates while re-atomizing the compound to generate my nitrobenzene substrate. Okay? So for practice, please practice the mechanisms of sulfonation, halogenation, Friedel-Crafts acylation, and alkylation of benzene. It's a good practice for you guys to practice all the mechanisms for all 5 classes of electrophilic substitutions. Okay, now let's study substitution effects, also known as directing groups. Let's review really quickly. I can react the benzene ring with an electrophile, and I generate resonance structures, 3 main resonance structures. I'm going to just kind of summarize all 3 resonance structures by this resonant hybrid structure here. What we see here is that neighboring carbons to our electrophile are going to generate this plus charge, so this carbon this carbon and that carbon. All right, and this is very important in studying or investigating substitution effects. All right, we want to be able to understand that certain groups are going to stabilize these carbons that have these plus charges, and other groups are not. And this is what's going to dictate how things are going to react. So now I'm going to take out my aromatic ring that has its extensuant now. So this becomes very important. So now I have an R group on the ring, okay? And this is going to start to lead to 3 new positions that we need to really investigate. All right, the first, I can have a 1-2 relationship to my substituent, or I can have a 1-3 relationship to my substituent. All right, the 1-2 is known as the ortho position, and the 1-3 is known as the meta. All right, there's still one more position, which is 1-4 with the substituent, and that's known as the para. All right, so now it becomes very important for us to keep in mind these 3 positions. All right, they have completely different reactivity, and it's very important for us to be comfortable with specifying ortho, meta, and para positions on a benzene ring. Okay, so let's kind of update our discussion of this resonant hybrid by now adding substituents either ortho to it. So I have electrophile ortho here, I have an electrophile meta here, and I have an electrophile para here, right? And we start to realize that there are some very important features that come out of this. If I look at the ortho position, I generate a carbon cation directly under this R group right here, right? And I do the same thing in the para position, right? Again, there's a plus charge right directly under this R. But in the meta position, I don't have the plus underneath the R, and those features there are very important. So now let's discuss. If R was an electron donating group, that's probably good to be right underneath a carbon that has a plus charge, right? Because I can donate electrons into that carbon with a plus, I can help stabilize it. But if I was an R that was electron withdrawing, that's bad. I already have a plus, and then I have another atom that's pulling electrons away. That's like 2 pluses wanting to repel each other. That's a very strong destabilizing effect. So let's take a look at that. So again, now I have an electron donating group. I'm going to erase some of this stuff here so you guys can have that clean. I'm sorry. So if I have this electron donating group and then add it into my 3 different positions, ortho, meta, or para, as we were saying earlier, now I have my electron donating group underneath this delta plus. For the ortho position as well as the para, I have an electron donating group underneath that, and that's a very good thing. So that's stabilizing both of these structures. So electron donating groups are going to favor electrophiles adding to the ortho or the para position. We just say that electron donating groups are OP directors. All right, all electron donating groups are going to favor electrophilic attacks at the ortho and the para position. Okay. So what do you think happens if I had an electron withdrawing substitution? Okay, we talked about that a little bit as well. This electron withdrawing group does not want to be next to these plus charges, right? So this destabilizes the ortho and the para position, and instead electron withdrawing groups only prefer the meta position. So we summarize this by saying electron withdrawing groups are meta directors. Okay, let's cover electronic groups after donating, withdrawing, and then we'll cover this new term of activating and deactivating. Okay, so electron donating groups are present here. The best way to summarize these are lone pair bearing atoms or other carbon groups. So up top we have our negatively charged oxygen, nitrogen, and sulfur species. Right now, underneath that, we have just plain oxygen species, so alcohols, ethers, amines. Okay, esters and amides are also donating groups. Eating carbon group, so straight chain, we get alkanes and alkynes. And then the halogens are electron donating. Again, it's pretty easy to see These are atoms that contain lone pairs or just other carbons that doesn't mind sharing their electrons with carbon cations. Okay, on the opposite end of this are electron withdrawing groups. Okay, we can summarize these by saying that these are groups that have polar pi bonds or electron deficient atoms. All right, so nitro are sulfonyl groups, protonated nitrogens, carbons that have trihalide, holoform type of substrates, ketones, aldehydes, and nitriles are electron withdrawing. Esters, acids, and amides, as well as acid halides, are electron withdrawing. Now, there's a trick here, or something that you guys can see. I said that esters and amides were electron donating, but then I said esters and amides are also electron withdrawing. It really depends on where you are attached to the ring. You are electron donating if you're attached to the aromatic ring at O or at an N in the ester or amide, but you are electron withdrawing if you are attached at the benzene ring by the carbonyl, the carbon-oxygen double bond. So keep that in mind. Esters and amides can swap, either being donating or electron withdrawing, depending on how they're attached to the aromatic ring. So let's talk about this activating and deactivating. And everything is pretty much studied from benzene. So groups that are going to increase that activity here. So we have this methyl group and you have this methoxy group added to the benzene ring. They're going to react faster than benzene, and we specify these type of substituents as activators. Okay, and groups like chlorobenzene or nitrobenzene, they actually react slower than benzene. So we say that those substituents are deactivators. Okay, so this is pretty straightforward. All of your electron withdrawing groups are deactivators plus the halogens. All right, and I know halogens are electron donating, but they are deactivators. Okay, and our activators are all electron donating groups minus the halogens. All right, so all of the other electron donating groups are going to activate the benzene ring to react faster than benzene. All right, so it's very important to keep this, I guess, level of knowledge or understanding of substituents in mind. Electron donating and electron withdrawing versus activating and deactivating. Okay, now let's practice. Could you give me the major product from these three reactions? And if you need more time, please pause now. Okay, for the sake of time, I'll move forward. The first structure has a CN, a nitrile, all right, and the nitrile is a meta director. All right, I got foaming sulfuric acid here, so this is a sulfonation reaction. So I should write SO3H in the meta position, which is a 1-3 relationship between substituents. The second reaction has a tert-butyl group, which is a regular alkyl group. All right, and alkyl groups are electron donating. So this is a OP director. Okay. For this, I get only one product. All right, even though I specify ortho and para, I get one product here, and that's because of sterics. Only the para product can be formed. The ortho product has very bad sterics, and it won't form here, so there's only one product. All right, the last problem here has a chlorine, and chlorine is a directing, right? So it's an OP, it's electron donating, it's an OP director, okay? And I have this acid halide with a Lewis acid. So this is Friedel-Crafts acylation here. And I'm going to get two products. I'm going to get the para position, and I'm going to get the ortho position substitution. Okay? So the next question that should come to your mind, what happens if I have two substituents on my aromatic ring? Okay? What do I do? Okay, so The two substituents, I like to call this competition among substituents. And there's 5 rules that we want to have down to really answer these questions correctly. The first rule is stronger electron donating groups would beat a weaker one. So if you guys go back to my discussion of electron donating groups, I gave a hierarchy among strong and weak. Typically, atoms that have a negative charge are going to be stronger donating groups than those that don't have charges. Next, oxygen, nitrogen, and sulfur compounds are going to be pretty strong donating versus oxygens or atoms that have carbonyls, right? Esters and amide. Next will be carbon. Regular carbon groups are pretty moderate in donating. And lastly, the weaker type or the weakest type of electron donating groups are the halogen. Because those atoms are very electron negative, they don't have a tendency to donate as well as oxygen, nitrogen, and sulfur type of lone pairs. Okay, so take a look at this case here. I have an ester up top. I have a hydroxyl group or alcohol on the bottom. Br2, FBr3 is bromination. So I'm going to get the bromo compound near the hydroxyl group because it's a stronger donator, right? Again, having an oxygen next to a carbonyl, those lone pairs are not going to be able to participate in donating to the aromatic ring because they are in resonance to that carbonyl. But the hydroxyl lone pairs are fully accessible to the aromatic ring. That makes it a very strong electron donating group. All right, so the stronger donating group beats the weaker one. Rule 2 says electron donating groups always beat an electron withdrawing group. So if I look at this molecule, I'm so sorry, I have a methyl and a nitro, and I have this CH3Br and this FeBr3. This is again Friedel-Crafts alkylation. All right, I'm going to alkylate next to the methyl group. The methyl is a stronger donator than the nitro. All right, that's a typo, not ester. Okay, rule 3. There's no possible substitution in between two substituents. So if I have this molecule here, this nitro-methyl benzene substrate, okay, and again I want to do Friedel-Crafts alkylation, I cannot go in between the two, which is ortho to the methyl. All right, so I got two substituents. The nitro group is a meta director. The methyl group is an OP director. The methyl group is electron donating, and the nitro group is electron withdrawing. Again, the donating group will win. All right, so I should go ortho and para to it. But one of the ortho positions is unaccessible in between the nitro and the methyl. So instead, I get, it's bad because of sterics. So I get these two products where the first is para to the methyl group, and the second is ortho to the methyl group. Okay, there's 2 more to go. 2 electron withdrawing groups give no products in electrophilic aromatic substitution reactions. All right, the arrow ring is 2 electron deficient to react. All right, to summarize that, if I had 2 EWGs, 2 electron withdrawing substituents on an aromatic ring, I'm going to automatically get no reaction, regardless of what class of EES you do. Okay, the last rule. Friedel-Crafts alkylation and acylation cannot occur with electron withdrawing groups. All right. So if I have 1 electron withdrawing group on those aromatic rings, they cannot do the acylation or alkylation reactions. All right. For practice, can you provide the major product from these 4 reactions? If you need more time, please pause now. All right, here are the answers to these products. Students in my class, there's a quiz due before class on Tuesday, and I will have office hours on Monday. I would love to speak more about these with you if you need more help. Best of luck.